Okay, so support vector machine, or SVM, is another popular machine learning algorithm that is mainly used for binary classification. So a hyperplane is trying to separate two classes with aim to maximize the margin between them. Particularly, we use some data points from the two classes. They're called supporting vectors, and the hyperplane tries to maximize the margin between them. So there exists also several applications for SVMs. For example, they are used to classify text based on its content, or even to distinguish between handwritten text from computer written text, face detection by classifying objects into face or non-face, and image classification. And finally, a critical application is cancer classification to check if it is malign or benign. Other famous machine learning algorithms are linear regression and logistic regression. And these two algorithms are similar. So both of them try to find the line that maps a given input to its correct output. And here we want to figure out the relationship between the input and the output. Well, linear regression is used for regression. For example, we can predict the price of a house based on its area. However, logistic regression is used for classification. So the output is a numerical value, but it represents the probability of belonging to a given class. For example, if it is less than a given threshold, 0.5, then it is class 1. If it is higher than this threshold, if it is class 2. This is for binary classification. So in this example, we have a logistic regression function that predicts if a student fails or succeeds based on study hours. Now, after training our linear regression model, we can use it in prediction. For example, for a house with 200 meters square, the price is going to be $12,000. In the same way, we can use logistic regression for classification. For example, if a student studies 4 hours in a day, then the probability of passing is 0.9, which is equivalent to the class label pass because it is higher than our threshold 0.5. Linear regression also has been applied to many areas, for example, sales forecasting, to predict whether the sales are going to be increased or decreased in the future based on historical data. They're also used to study the effect of water on the amount of crop, also in sports to understand the correlation between weightlifting and player scores in NBA. And finally, in medicine, to study the relationship between medication consumption and blood pressure. Logistic regression is also widely used in real-world applications, or it has many real-world applications, namely in email classification into spam or non-spam based on their content, online shopping to recommend a product to the user based on his data. Also in medicine, for example, could be used to predict the effect of smoking on having a lung cancer. And finally, in electronic transactions, to study the relationship between the amount of transaction and the probability of a given transaction being fraudulent. Now let's talk about deep neural network. So a deep neural network is also a machine learning algorithm, which is composed of individual units, and they are called neurons. And they are organized in several layers, as you can see. So when data is input to the neural network, it propagates through these neurons until it is transformed to the desired output. So the role of a neuron is that it receives an input, processes it, and outputs the processed input. And a layer is composed of several neurons that belong to the same level. The weights, depending on their values, determine the strength of a connection between two neurons. So we want to give certain importance to the information that propagates through this connection. To understand more clearly what happens inside a neuron, so a neuron receives one or several inputs from the previous connected neurons. Each input is multiplied by its respective weights, depending on the connection, and then all these inputs are summed and passed to an activation function. And the role of an activation function is to activate or deactivate this neuron in order to emphasize or de-emphasize the propagation of information through this neuron. And this is an example of application of a neural network. If we are interested again in predicting house prices depending on their characteristics, then our inputs are the features of these houses. The number of neurons of the input layer equals the number of features. So we have 3 features, and this is why we have 3 neurons in the input layer. And then these features are passed through the network and processed by neurons until we can get the output. And here you can see that the output layer has only 1 neuron because we only have 1 output to predict, which is the price. Now, let's see the different layer types that exist within a neural network. So we have the fully connected layer, also called dense layer. And this layer is fully connected with its previous layer, meaning that each neuron of this layer is connected to all the neurons in the previous layer, as you can see in the example. A batch normalization layer normalizes the data that is passed through the network by putting them in the same scale, and this is done per batch. Well, a batch means data samples that are passed through the network at a single time, and I will explain this more later. So this makes the neural network stable and able to better learn from the training data. Convolutional layers are used for image processing, so their role is to extract relevant features from images using filters. They are 2D metrics. So each neuron in the convolutional layer has a filter to extract a specific type of features. Pooling layers are usually used right after convolutional layers to reduce the feature size. As you can see in the example, here we have an example of max pooling. So we select the max value from a given portion of our image. And LSTM layers, they are used in LSTM neural networks to extract useful features from sequential data, for example, speech or text. And finally, flattened layers that transform 2D arrays to 1D array before passing it to the fully connected layers or the last layers in the neural network that perform the classification task. So these last layers expect a one-dimensional feature vector, so we should flatten our data before passing it to the fully connected layers. Well, we said previously that each neuron passes the weighted sum of inputs to an activation function, and this function activates or deactivates this neuron. So here are some examples of the commonly used activation functions. So first we have ReLU activation function that is commonly used in the hidden layer. It transforms negative inputs to 0 and does not change positive inputs. The second one is sigmoid activation function that is used in the output layer for binary classification. So when we only have 2 classes, the output value is always between 0 and 1. And the last one is softmax activation function that is used for multi-class classification. And it is also used in the last layer and outputs a value between 0 and 1. Well, the important thing to mention here is that these functions are nonlinear. So you can see that the relationship between x and y axis is not aligned, so there are no linear functions. And this makes the neural network a nonlinear algorithm. Well, this property enables the neural network to detect nonlinear relationships between inputs and outputs. For example, if we think about image or speech classification, then the relationship between the data and the class is nonlinear. And this is one of the reasons that makes neural networks well suited for this kind of task or data. We've already discussed the parameters and hyperparameters, and we said that parameters are set and optimized by the algorithm, while hyperparameters are set by the users. So for a neural network, the parameters are the weights and the biases. We've already talked about the weights and said they are optimized during the training phase. In addition to the weights, each neuron has a bias, and that is also a trainable parameter that allows the network to better learn from the training data and to be more flexible. Regarding the hyperparameters, well, they are set when we create our model, and the hyperparameters in a neural network, so we have the learning rate, which determines the speed of training. In other words, how much we change the weights values when updating them. We also have the architecture of the neural network, for example, the number of layers or neurons. The batch size is also an important concept to understand. So it is the number of samples that we pass together to the neural network while training it. So for example, if we pass 10 samples in a single forward pass when training the model, then the batch size is 10. On the other hand, an epoch is a single pass of all the training data samples. So an epoch is basically composed of several batches in case the batch size is less than the training data. So the number of epochs is the number of passes of the full training data. We also have the optimizer, that is the algorithm used to train the neural network. And finally, the loss function that we have already discussed. So these are examples of hyperparameters that could be tuned to build a more powerful neural network. Now that we understand the architecture of a neural network and the main terminology, we can get back to our example and see how a neural network is trained. So suppose we have a database of houses features and we want to train our neural network to predict their prices. The first step is called the forward propagation, and here data is passed and processed through the network from the input layer to the output layer. So a given neuron G receives the outputs of other neurons as inputs. Then it calculates the weighted sum and passes it to an activation function, as I explained previously. And then it outputs the process data. Well, this process data continues to propagate forward in the neural network, now as an input of a next connected neuron, and so on, until the output, which is the price, is computed. So assuming that the learning is supervised, then the loss can be computed based on the difference between the correct output and the correct output and the predicted output. And at this stage, it is time to start moving backwards. So we are going to do the backward propagation. Now our aim is to optimize the values of the weights in order to minimize the loss function. So given an individual data sample, we compute the gradient or the derivative function of the loss with respect to each weight. We start by the weights at the last level and compute the gradient for each weight. And then we move backwards and compute the gradients of the weights at the previous level. And so on, until we compute all the gradients. And now each weight is updated using its corresponding gradient. Here you can see the formula. So we have to multiply the value of the gradient by the learning rate and subtract it from the actual weight to get the new weight value. For example, for weight 1, we move from 0.23 to 0.19. This is just an example. And we do the same process for all the weights. So this was the process of one training iteration. Now, with these new weights, we can pass our data again to the network, doing the forward pass or the forward propagation again, and then optimize the weights again, doing the backward propagation. And we keep doing this process again and again until we reach a minimum value of the loss. So in the previous example, we've seen how to train a neural network from scratch. There is actually another way to train a neural network or a machine learning model that is called transfer learning. So what is transfer learning? Transfer learning refers to using the knowledge of a given model learned from a specific task and applying it to another similar task. So as you can see, in the traditional learning process, for dataset A, we train a model A on this dataset. Now, if we have a new dataset referred to as dataset B and taken into account that this dataset is similar to dataset A, then we need to create a new model and train it from scratch. If we use transfer learning, we don't need to train model B from scratch. Well, say that we've already trained the model A on dataset A, and dataset B is similar to dataset A. In this case, we can use the knowledge of model A to create model B. So this is instead of training it from scratch. And what we mean by knowledge is parameters and also hyperparameters that we have already tuned when building our first model that we refer to as model A. So there are several reasons to do this. The reuse of this knowledge can greatly reduce the computational cost required to create or train the second model. And it is also very useful if you don't have enough data to train the new model. So one way to do this is called fine-tuning. So let's see how to use transfer learning or fine-tuning with a neural network. And this is a real example that is actually used in convolutional neural networks. So suppose that we have a dataset of 1 million images that is called ImageNet dataset, and this is our first task. So we have already created a model to classify images from this dataset into 1,000 categories. And this means that we already have a model or a neural network that was trained on a huge and diverse dataset. So our neural network has already learned a lot of diverse knowledge about the different patterns that may be included within images. Now we have a new dataset for cats and dogs, and this is our new task for our new dataset. So we want to create a model to classify an image into two categories. We have cats and dogs. So instead of training a neural network from scratch, we can use the previously trained model that has already seen a large number of categories, including animals. And we just adapt it to our new dataset of cats and dogs. So what we do is to freeze the early layers of the previous neural network to keep their weights or knowledge. So these layers are not going to be trained, and this is what we mean by freezing layers. And we replace the last layers by new layers with respect to the number of categories. Here we only have 2 categories instead of 1,000 categories. And then we train these layers on our new task, and this is called fine-tuning. So the new fine-tuned network is now ready to predict whether an input image is a cat or a dog. So you can see this way that we can use the previously trained model on ImageNet with several image categories by just fine-tuning it. And this is because it has already seen a large number of different images. So this was about fine-tuning and how and why we use it. Now, let's see some types of neural networks. We're going to start by convolutional neural networks. So the main property of these networks is that they are able to extract features from images without losing the spatial information that exists in the image. So what we mean by the spatial information is the relative position of pixels. In more simple words, we can say that the arrangement or positions of patterns that exist within the image is kept. So you can see in this graphic the output of each layer in the CNN. So we have the input image that passes through the convolutional layer that I explained previously, and this layer outputs different representations of this image by keeping the spatial information, and they are called feature maps. After that, these feature maps are passed to a pooling layer. So the output of a pooling layer, as you can see, is reduced feature maps. So the pooling layer performs dimensionality reduction. And then these reduced feature maps are flattened or transformed into a one-dimensional feature vector, as I explained previously, and they are processed by the fully connected layers to perform the classification. And finally, the output layer displays the classification results. So this is how we move from an input image to a vector of probabilities to classify the input image. Another popular type of neural networks are LSTMs. They are a category of recurrent neural networks, so they have recurrent connections, and they are used to process sequential data such as speech or text. Well, if we speak about text, for example, then the text is input character by character. And thanks to the LSTM neuron, they are able to learn useful features while keeping the network stable by preventing the vanishing or exploding gradients. So without getting too much into the details, the vanishing gradient problem occurs when the gradient of the loss with respect to the weight that we computed previously. So the vanishing gradient occurs when this gradient becomes very small. And the exploding gradient occurs when this gradient becomes very large. And this makes the neural network not able to reach the minimum value of the loss. So this problem occurs in traditional recurrent neural networks. LSTMs solve this by controlling the flow of information through an LSTM neuron. So this cell has 3 gates. You can see the input gate to decide which information to input, the forget gate to forget information that is not necessary or redundant, and the output gate to only output the useful data that contributes in the final classification, for example. So this way, the LSTM cell gets rid of redundant and unnecessary information and only keeps the useful data. GANs are or generative adversarial networks are another type of neural networks, and they belong to the generative models. So this means that based on inputs, they can generate new different outputs. They are composed of two CNNs. We have the generator and the discriminator that compete one against another in order to generate new samples based on training data. Well, I think GANs are undoubtedly one of the most fascinating neural networks, and they have very useful applications. So they could be used to create more samples of training data, data augmentation, image enhancement, to improve the image resolution, video predicting, to predict the next sequences in a given video, etc. So in order to train a GAN, first, the discriminator is trained on a real data set to learn how to distinguish between fake and real samples. And then the generator generates a new image by adding random noise to the training sample. So the generator creates a fake image with aim to fool the discriminator. After that, this generated image is passed to the discriminator to classify it as real or fake. And these steps are done again and again until the GAN can generate fake samples that they are classified as real by the discriminator. So they are fake images, but they look like real images. And this is the purpose of a GAN. I just want to show you how fascinating these networks are. So look at these images. They look so real, but they are fake images or fake faces, and they were generated by a GAN. Now, the last example that we will review are autoencoders, and their aim is to learn a reconstruction of an input data. So the input data is compressed using the encoder, and then reconstructed using the decoder based on the compressed representation. So autoencoders are unsupervised methods, and they try to learn the relevant patterns that exist within data. And they have been successfully used for image denoising, compression, feature extraction, etc. Okay, now to the final section in this presentation, we are going to make an overview of some advanced machine learning techniques called ensemble methods. So in these techniques, multiple machine learning models are used to predict the output of a given input data sample. And there are several ways to create an ensemble of diverse algorithms. So the first one is to use a different training subset to train each model. And this results in models with different parameters. Second, we can use different algorithms in terms of architecture, for example, SVMs and decision trees. And finally, we can use the same algorithm with different parameters, for example, neural networks with different weights values or weights initializations. And here is an illustrative example. So if we want to predict the class of a given image, we can pass it to the ensemble of machine learning algorithms. Then each algorithm is going to predict a different output. And then we can combine these outputs to make the final prediction. So why do we use ensemble methods? Ensemble learning methods are known to be more accurate than individual classifiers. They reduce the bias and/or the variance depending on the method, and they also enhance the output for a given data sample. And I will show you an example of this in a moment. If we speak about the drawbacks, then they are less interpretable. So this means that due to the diversity of the included algorithms, it is difficult to track the output and understand how it was generated. The other thing is the increased computational cost when compared to a single model. So we need to train several models instead of one, and Also, the prediction is made several times depending on the ensemble size or how many algorithms are in the ensemble. I just want to show you an example to understand how ensemble learning improves the final prediction. So suppose that we want to classify this input image as a cat or a dog. The final output represents the probability of belonging to the class dog. So this is binary classification. So if it is higher than 0.5, then it is a dog. If it is less than 0.5, then it is a cat. The first model outputs 0.2, which corresponds to the cat class. So it is a wrong prediction. Now, if we only lean on these classifiers to classify this image, then the output is false. Now, let's check the outputs of other classifiers. Well, we can see that two models correctly classify our input image. So averaging all these predictions will lead to a final correct prediction since it is higher than 0.5, which means a dog. So generally, most of the included algorithms output correct predictions, especially if you are using neural networks, because we are using powerful models. So this is why the final predictions are improved. Well, hopefully you have now an idea of how this works, and you can see that using an ensemble may rectify the false predictions of individual classifiers. Now, let's review some ensemble learning methods. So the first one is the bagging technique. Herein we can create several models that may have the same architecture, and we train each model on a different training subset built with replacement, and it is called a bag. With replacement means that the same sample may be selected more than once in the same bag or a different bag. The bag size is less than the original training set size, and each bag is fed to a model as a training set. So we will have as a result an ensemble of diverse models since they were trained on diverse training subsets. And we can use this ensemble to predict diverse outputs for a given input and then combine these predictions to make the final output. Well, in the bagging technique, note that the models can be trained in parallel or simultaneously. Second, we have boosting. So boosting is similar to bagging, but the difference is that the models cannot be trained simultaneously. So first bag is created and used to train the first model. After that, the training data is passed to this model to predict its outputs. And then we can identify the wrongly predicted data samples and use them to create the next bag of data. You can see that the next model will have more focus on the wrongly predicted samples. And here we want to correct the outputs of the wrongly classified samples by the previous classifiers. So this is what we do in boosting, and this is why it is sequential and cannot be done in the same time. Or the training of the models cannot be done in the same time. So we repeat the same process again and again until the full ensemble is trained. And finally, the trained ensemble can be used for prediction, just like the bagging technique. The last ensemble method that we will cover is called stacking. So it is a bit different from bagging and boosting. In bagging or boosting, the outputs of classifiers can be combined using the average or the median, for example. In stacking, the combination of outputs is learned by a meta model. So first, we need to split our data set to train and validation data. Then we can assume that we have an ensemble of algorithms with different architectures. So each algorithm is then trained on the training data, and after that, the validation data is passed to the ensemble to predict its outputs. And at this level, another machine learning model will be used to learn how to combine the classifier's predictions. And this is done for each individual sample. So this model is called a meta model, and a meta model is a model that learns from the outputs of another machine learning model. So the meta model here learns from the predictions of the ensemble of machine learning models. Also, this meta model assigns a weight to each classifier that represents its performance or contribution in the final output. So the final output is the weighted average of all these classifiers. So you can see that stacking is more sophisticated when speaking about the combination of the outputs of the ensemble of models. As final thoughts, let's make a recap on how to create a machine learning model. So the first step to do is to collect data, and this is a very important step because no matter which model you choose, its performance depends a lot on the training data. So always make sure you have a large enough and diverse data set. Second, we need to pre-process our data. For example, removing noise from data or scaling it to put all the features in the same range. And this is also very important to create a stable model. Also balancing the data set. If one category is significantly larger than another, then the model is going to be biased or more biased towards this category, and it will have less focus on the other categories. The third step is about choosing the right model, depending on the problem at hand. And here you may ask a lot of questions about the learning type. So, for example, is it supervised or unsupervised? Is the data set linearly separable? If yes, then I can use a linear model such as an SVM. Do I have a large data set? If yes, then I can use neural networks because the performance is good when we have a lot of data. So depending on all these characteristics, we can choose the model that best fits our problem.
Again, so sorry for interrupting you, Safa. Yes. We need to reconnect again. So dear participants, please try to reconnect right now. Okay? So sorry, doctor, for this interruption.
No problem.